Okay, I think we can start now. Yeah, first of all, thanks to the Rasa team for having me at this conference. I'm really honored that this is possible, and thanks for the awesome organization. Yeah, before we start into my talk, how to build a smart speaker powered by Rasa, I'd like to introduce myself. My name is Julian Gerhard. I'm currently 33. I have been working as a software developer for almost 20 years now, and in the field of digital speech processing for almost 8 years now. During my studies for being a teacher, I developed a love for language, and in combination with software development, I have made it my mission to improve human-machine communication. When I'm not sitting at the computer, I like to read, do sports, teach my dog German, and drink lots of coffee. Currently, I'm working for the company Susie and James in Mannheim near Heidelberg in Germany. The company was founded in 2014 and has set itself the goal of digitizing and optimizing business processes with the help of digital employees. One of them you can see, it's called Susie, our first digital employee. And currently there are about 30 employees, of which 12 developers responsibility. To give you a short impression of what I usually do, I brought a short project example with me. Imagine that you build expensive vehicles and are dependent on absolutely safe, traceable quality control for every single component and the entire assembled vehicle. For this quality control, it is necessary to drive the test driver with the car over a test track and to work through a quality control protocol. So far, whenever the driver notices something unusual, he has had to stop the vehicle and take notes. Although he now uses a tablet for this purpose, he still has to enter those notes by hand. Our task was to use voice input in the vehicle, not only to enable the driver to enter a note while driving, but also to use classification procedures to determine the department that would later be responsible. There were numerous difficulties, such as interference with speech recognition due to noise, but the system was successfully tested recently. Here is a sample dialogue depicted. Hey, Susie, what can I do for you? I want to create an incident report. Then Susie says, sure, please describe the incident. And the driver says, for example, with approximately 200 kilometers per hour, the right front outside mirror begins to rattle, something that should not happen. Okay, I have set a trigger to persist the vehicle configuration for the past 3 minutes. So that's just to give you an idea of what kind of tasks we are trying to accomplish. So now let's dive into the matter, how to actually build a smart speaker. When I asked myself this question, I noticed that there are other important questions. Do you actually build a smart speaker that is powered by anything? How do you build a smart speaker? Since I'm not an engineer, the very basic question also arose, how do I build anything at all? Two basic approaches came to my mind. You could look at existing devices, unscrew them, and take a close look at their construction in order to be as smart as possible. The disadvantages are obvious. On the one hand, you will probably render the devices inoperable. On the other hand, this approach is expensive and you learn too little about the software. The second approach seemed to make much more sense. I should think about the project and approach it step by step. This will probably take longer and could prove to be challenging, but you learn a lot more and can possibly impress others afterwards. So if you think about the project in more detail, it is best to sort all the modules that play an important role at the beginning. Among them are the obviously necessary technologies like automatic speech recognition, speech synthesis, and of course the artificial intelligence behind it, but also more basic topics like power supply, maintainability, and last but not least, the hardware itself and optics. For me, it has proven to be practicable to simplify a problem in order to approach it step by step. I have therefore divided speaking with a smart speaker into 4 simple sub-applications: voice input, transcription, AI processing, and voice output. Therefore, a microphone, software, and a speaker are necessary. As initial components, I bought a ReSpeaker microphone module, a Raspberry Pi 3, and a simple jack speaker. The ReSpeaker module has 4 microphones mounted on the outside and a ring of 12 LEDs to visualize the processing status. The Raspberry Pi 3 was at that time a simple model with only 1 GB memory. The speaker was the cheapest I could find on Amazon, and its main feature was that it didn't need an external power source. Once I had all the necessary parts together, I assembled them and used them to create the first simple prototype of my smart speaker. The backend consists of a control software which embeds input, processing, and output in a sensible sequence, and of course a Rasa bot, which was quite simple at that time.
Hey Susi.
Hallo Julian.
Hey Susi.
Hallo Julian.
Was sind deine Funktionen?
Ich kann Nachrichten hinterlassen und Termine vereinbaren. Kann ich noch etwas für Sie tun?
Hey Susi.
So basically, this was a sample in German. I simply asked the bot about its functions. You see, this is a complete working sample for the first one. When the prototype proved to be actually working, it was time to build a case for it. The case came from a 3D printer and was made to fit the parts. Once the case was finished and all the parts were properly installed, I did a kind of inventory. The first version of the speaker was finished in December 2018 after about 1 month of work and cost nearly €200 without working time. Due to unfavorable architecture, a real dialogue was very difficult to achieve because the decentralized backend caused high latencies and the range of the microphones was very limited due to the way they were mounted. The speaker worked, but the sound was anything but pleasant and the cabinet started to melt after about 10 minutes of continuous use. To be fair, I have to say that the unit worked surprisingly well.
Hey Susi.
One could of course be satisfied with that now and say, great, task accomplished. But since I'm basically one of the more ambitious types, I wanted to build a second version of the speaker to compensate for the shortcomings of the first version. The speaker, whose creative process we will see in a moment, was finished 1 year later, in December 2019, cost about €800 without working hours, and its production took almost 2 months.
My new case is made of high-quality mahogany wood and a cover of fine fabric printed with our company logo.
That looks pretty solid, don't you think? Let's just look at what's under the hood. Voice recognition consists of two modules. As you probably know, most commercially available smart speakers work with so-called hot words, terms that you have to name before you say what you want to say. On Amazon's Alexa speakers, this would be something like, "Hey Alexa." On Google Home, for example, "Okay Google." That just actually triggered my own Google Home. I implemented this method with Snowball because the underlying model is easy to configure and is characterized by very low power consumption in continuous operation and short processing times. In the case of transcription, the device currently works with the Google ASR cloud, but offers an interface for the other well-known providers like IBM, Amazon, and Azure. An experimental version of the software also has an ASR system trained on the Mozilla Common Voices dataset itself to work offline. The problem here was to gather enough data for the German language, which is really kind of tricky, but it worked out in the end, but really not the same quality than Google and Azure could provide. The speaker also has a direction of arrival recognition, which, like an Alexa, indicates the direction from which the speech is being recorded via the LED ring. The core is a Rasa bot, still in version 1.4, shipped on a Debian 10, which is addressed and controlled by a self-written control system. Some of you may know that it is not so easy to install arbitrary libraries, the whole stack necessary for processing on a Raspberry Pi with limited resources. Rasa has its own thread for this, which I can highly recommend. Last but not least, speech synthesis currently uses a German WaveNet voice from Google, but Amazon's Polly can also be connected. The processing of the speaker is basically quite simple. It listens until someone pronounces the wake word. The speaker then responds with an auditory signal and accepts the request. The control system then sends this request to the bot. The bot generates an answer, and the control system delivers the answer to the user via synthesis. An important distinction is that the smart speaker is truly dialogue capable. That means the bot knows whether a user input will result in a consecutive input or not. This means that the speaker does not switch back to its original state after output, but listens again. Due to the limited resources, I had to do different tests with different bots to find out the natural limit of the software. I started with just 4 different intents and a very simple pipeline for the English language, which meant a short training time and very good latencies. The second model was trained on the German language with 17 different intents and about 35 examples per intent. With 15 minutes training time and a small model size, this was still a good result, but the average response time of the bot had more than doubled. Last but not least, I wanted to take the chance and train a bot with 228 intents, nearly 400 examples per intent, and over 1,700 stories on a pipeline with the transformer approach. Since the training already caused memory problems, I swapped the whole thing out and tried to just execute the model, which also wasn't successful. After this result, I stopped working on the device for the time being, but I will resume it shortly to incorporate more functions. So that you can get an idea of the actual working speaker, I'd like to show you an example. It's just a small video I recorded. I hope you can hear everything. And yeah, just to let you know that the device I'm talking about actually exists.
Möchtest du, dass ich dir einen Betrag abgebe?
Ja,
Ja, ich würde da einen Wegfahrer empfehlen. Die Zubereitung ist auch recht einfach. Süße und Gerhard mit Eiswürfeln und in ein Cocktailglas abseilen. Die Zitronenschale hinzufügen und servieren. Du benötigst dafür folgende Zutaten: süßer Wein und Schälchen und Zitronenschale.
So basically what you've seen now is me talking to the speaker, asking if the speaker could recommend a cocktail, and the speaker recommended a blackthorn cocktail and described how this one could be, how you could create this cocktail.
lass uns Was ist was spielen.
Welchen Begriff soll ich dir erklären?
Kontradiktion.
Eine Kontradiktion aus lateinischen Kontrari und lateinisch Diktion, das Sein und Leben den Widerspruch liegt in der Logik vor, wenn zwei Begriffe, Urteile oder Aussagen im Widerspruch zueinander stehen und eine gegenseitige Negation darstellen. Gegenteil und zwar Kontradiktorisches ist der konträre Gegensatz.
Yeah, so now you've seen a working example. What happened is just I asked the speaker to explain a word for me, and I wanted the speaker to explain the word contradiction, which I really like. Maybe you've seen and observed that the latency is still very high. That is because in this video the bot is hosted on my laptop and not on the speaker itself. That's something I'm currently working on because it's not that easy to install dependencies on the latest Debian, and there were lots of issues that I'm currently working. But to be able to show something, I've simply outsourced the bot itself. Yeah, now I hope that you enjoyed the lecture and the talk, and maybe I've even inspired your own areas of applications with that. And I'm open for questions, and I hope you had a bit of fun.